Hi, everyone. Thanks for coming. My name is Joshua Falk. I'm a data scientist at Civis Analytics. And today I'm going to be talking about generating realistic, differentially private data sets using generative adversarial networks. In case it's easier for you to follow along or you just want to see the slides afterwards, they're online at bit.ly/DPWGAN, all in caps. So before I get into what each of the parts of this title means, I want to sort of motivate what I'm talking about with a problem you might encounter. So the problem is, how can we make data available to research, but also protect the privacy of people who appear in the data? So to give an example of what this might look like, maybe you have medical records, and you want to make these medical records available for researchers so that they can, improve patient outcomes, develop new cures, things like that. But medical information is often very sensitive, and people might not want their personal medical records just to be out there in public for anyone to see. So how can we balance these concerns? Or similarly, maybe you do a study where you're surveying people about who they plan to vote for. And again, that could be very valuable for political science research, but people might not want their voting intentions to just be out there for anyone to see. So how can we take this kind of data, make it available for research, but also protect the privacy of the individuals whose data appear in the original data? So there's a number of traditional approaches to solving this kind of a problem. One approach is to aggregate or summarize the data in some way, report summary statistics, maybe means or medians or standard deviations. You might group by certain subgroups in the data. But among other problems with this approach is that it really limits the analyses you can do, right? So first of all, throwing any sort of more advanced machine learning techniques onto this stuff is going to be really hard. And you also kind of have to guess in advance what people are going to care about. So maybe you divide your data by one group, but someone cares about another grouping. They can't do anything about it once you've released that data. Another approach that's out there is to add noise to the original data. And again, so if you have continuous values, maybe you add some Gaussian noise to the data. Among other problems, this really diminishes your utility. So this basically destroys almost all of the information that's available in the original data if you're going to do it in a way that actually protects privacy. And a last approach that used to be really popular, fortunately is becoming less popular as people recognize its limitations, is removing personally identifying information. So this is things like full name, date of birth, address. So you might say, oh, we'll just strip your name and address and date of birth from the data, and now we won't be able to identify you. You'll have privacy. But it's well known that this usually or often doesn't really work. And the reason is there's a risk of what's known as a re-identification attack, where maybe your name isn't in the data set, but there still might be information in the data set that uniquely identifies you. And so if someone can figure out which record is yours, then they can learn new information about you that way. And just more broadly, most of these techniques, it's often very hard to fully analyze and understand the kind of privacy that they offer and make real guarantees. So today I'm going to talk about an alternative approach that tries to get away from some of these problems. And the basic idea is instead, we're going to generate fake data, synthetic data, that's going to be individual level data, and that's going to look like the real data that we started with, and it's going to preserve important statistical information from the data so that people can research with it. So how does this help with the problems we saw before? So for the problem of limited analyses, because we're producing individual level data, this mostly goes away, right? The data is sort of in the same format as what came in as the real stuff, and so any analysis that you could have run on the original data, you can run on this fake data. The diminished utility issue that we saw with adding noise, we'll see that you need much less noise with this kind of an approach to still protect privacy. And so we'll be able to have data that has much more information in it. And with respect to the risk of a re-identification attack, because there are no real people in the data, right? These are all fake entries. There's not really a notion of, oh, this record belongs to this real person, so I identify them and then I learn new information about them. Now, all of this being said, generating synthetic data on its own is not enough to absolutely guarantee privacy. And so later in the talk, I'll talk about why that's the case, and I'll talk about the specifics of the approach that I'm taking that do allow us to have real privacy guarantees. But this is the broad outline of why this sort of synthetic data approach is appealing. So with that sort of problem motivation, I want to give you an outline of what the talk is going to look like. So in the first part, I'm going to introduce differential privacy, and that's going to be the framework that I'll use to sort of analyze the privacy guarantees and make privacy guarantees about the data sets that we generate. Then I'm going to talk about generative adversarial networks, which are a type of neural network, and that's going to be the technique that I use to make the fake data. I'll talk very briefly about a Python package that I've written to implement these techniques, and then I'll apply the package to some data from the census, some individual level data from the census, and see how that data compares to the real stuff that we used as input. So to start out with differential privacy, how we guarantee privacy. Rather than start with a definition of differential privacy, I'm going to give sort of a toy example where we work our way up to providing this kind of privacy guarantee and then sort of explain how it works. So here's the toy example. Let's say that you have a database of age information about lots of different people, and you want to make this information available to people in some useful way, but you don't want to reveal the age of any one individual in the data set. We're just going to treat age as a sensitive attribute for our purposes here. So here's a possible first solution. Maybe you only allow querying averages. So if this were like some sort of SQL language, you could say, you know, select average of age where some condition that you want met, and then you return that average. Okay, there's a bit of a problem with this, which is we can say something like, what's the average age of people named Betty White? And if there's just one Betty White in your data set, you'll get the average of her age, which is 97, and now we have this one individual's exact age. That's not good, right? We've leaked information about this person. Okay, now this might seem kind of silly, right? You're like, obviously when we said average, we didn't mean average of one, we meant average of a group. So maybe you place a little restriction on this. And now you say, when you query that average, the group you're looking at has to have at least 50 people. So right before we do the query, we count how many people satisfy the like where clause. And as long as that number is greater than 50, then we allow you to make that query. So let's walk through an attack that will show that even this approach isn't quite going to be enough. So first we see how many people are named Betty White or John. And let's say in our data set there's 96 people who meet these conditions, right? That's more than 50. Great, we can take the average. And we ask how many people are named John. In our data set, that's going to be 95, because there's only one more person named Betty White. Also more than 50, so we can ask about the average. So now we query for the average age of these two groups, and we get that the average age of people named Betty White or John is 49.5, and the average age of people named John is 49. Now we can take all these numbers and get two more pieces of data. We can get the total age of people named Betty White or John by multiplying the average by the count. And we can get the total age of all people named John by, again, multiplying the total by the count. And if we take the difference, we get the total age of all people named Betty White, namely the total age of the one person named Betty White, 97. So once again, we've leaked information about an individual, even though in theory we thought, oh, we're only querying averages of large groups. So it turns out we can make a slight modification to this algorithm, this technique, to ensure privacy. And how's that going to work? Again, we're going to say you have to query at least 50 people when you're asking for the average. But then, rather than returning the exact average, we're going to add just a little bit of noise to the result. So in this case, just for the sake of this example, let's say like some Gaussian or normally distributed noise centered at 0 with standard deviation 0.25. So very small. You're going to be like at most a year off with your average. So you're going to get some useful information out of the queries, but there is this little bit of randomness. So what happens when we try this attack that we did before with this modified algorithm? Do we still have a problem? So first we take the average age of people named Betty White or John, and we get the true value 49.5 plus this little bit of Gaussian noise. So in this case, we got 49.9. So that's pretty close for a lot of applications. That's going to be good enough. That's going to be high utility, give you the information that you need. But it's a little bit different than the true value. And then we're going to take the average age of people named John, again, plus this little bit of noise. We get 48.8, again, pretty close to the true value. But now notice what happens when we multiply by the count to try to get the totals out. So once again, we get something whose mean is the actual value we want, namely the total age of people named Betty, White, or John. But now the noise, the standard deviation, has been scaled by this count that we multiplied by. And so now all of a sudden the noise is actually quite significant, right? Centered at 0, standard deviation 24. That's like pretty large when you're talking about the age of a human being. And the same thing happens when we multiply the average age of people named John by the count of people named John. We get this quite significant noise. And so when we take the difference, we do get something whose mean is Betty White's age, but again, with this very significant noise added on, we get an age of 154.4, which is obviously not Betty White's age. And so we've successfully blocked the attack. We cannot recover the age of this individual. Okay, so why does this work? At its core, what's going on here is that the contribution of Betty White's entry to this average query is negligible relative to the noise. So her entry does contribute. In an aggregate, everyone's entries contribute in a way that gets you something very accurate. But as a single individual, your contribution just doesn't do that much. The noise sort of dominates. And that gives you the privacy. And this is essentially the core of what differential privacy is. So differential privacy is a property of algorithms, and it limits how much the output of your algorithm can change based on whether your data is included or not. And that's the differential part of differential privacy, right? So whether we include Betty White's data in this data set or not doesn't change the output of that average query all that much, because the noise is sort of the larger factor. And this also means that there's a limit to how much you can learn about a person because their data was included. And it also limits the confidence you can have about whether a person's data was included. And so this is the way that we're going to guarantee individual level privacy. Now, before I move on, I just want to give a couple of important caveats about differential privacy. The biggest one is, you'll notice that I've said individual privacy. Differential privacy, as typically implemented, doesn't provide any sort of guarantee about privacy for groups, and that can be important. So, for example, you could conduct a study where you learn about the average incidence of Tay-Sachs in some subgroup, and there might be reasons that some group might not want you to learn that information, right? So marginalized groups might not want to participate in your study or your survey despite your individual privacy guarantees, and that's completely reasonable. And so you want to think about, if you're going out there and you're going to be applying privacy techniques to your data, you want to think seriously about what you're trying to accomplish and what your needs are. And differential privacy is just one of several frameworks out there, and the right one is really going to depend on your needs. That being said, differential privacy does give really nice guarantees for individual level privacy and is in many ways very easy to analyze mathematically. And so that's what I'm going to focus on for this example. Okay, so I've shown you how to make this average query private, but of course one of the big motivations of this talk was to say we don't want to just report averages. We want to have individual level data, right? So how do we move toward individual level data? So in the next part of the talk, that's what I'll be discussing. I'll be talking about how we can make fake individual level data, and the tool we're going to use for that is generative adversarial networks. So now I'm going to give a quick introduction to this technique. So generative adversarial networks are basically neural networks, and it's a technique for training a neural network to generate data, hence the generative part. And it's actually the combination of two distinct neural networks, one network called a generator and one network called a discriminator. The generator network is going to learn to make data that looks like the real input data. And the discriminator is going to learn to tell the difference between real data and the fake data that the generator makes. And you're going to alternate training these networks, and they sort of battle it out and try to outwit each other. And that's sort of the adversarial part of generative adversarial networks. So I'm going to give a sort of toy example of what this training might look like. And the example that I'm going to use is generating digits, handwritten digits from the MNIST dataset, if you're familiar with that dataset. If you're not, it's just handwritten images of digits. So the generator is going to take some random noise as its input, illustrated here. We pass it to the generator, and it's going to make a fake image of a digit. Now, notice to start out with, right, the generator doesn't know anything. It's just like a random network. And so it's just going to output this random garbage that doesn't look like a digit because it hasn't learned yet. we're going to take the fake data and some real data, and we're going to feed it to the discriminator network. And notice again, at this point, the discriminator doesn't really know anything, so it just kind of guesses at random. Maybe it says they're both good, I don't know. And so now we're going to update the discriminator and say, hey, no, the top one is fake, the bottom one is real. Update your parameters and try to do a better job of distinguishing these two. So now once again, we take some random input, pass it to the generator. Again, the generator hasn't really learned anything. Pass the fake data and the real data to the discriminator. And now at this point, the discriminator knows some things, and so it can say, oh, that top one is fake, that bottom one is real. So discriminator is doing okay, generator is not doing so well. So we're going to tell the generator, hey, you should make stuff that the discriminator is going to like, the discriminator is going to think is real. And we update its parameters based on that. So now we take some more random noise, pass it to the generator, and notice now it's making something that, like, if you kind of squint, it kind of looks like a digit, right? You can see the outline of a 4, a little bit less randomness in there. So we take that, the real data, pass it to the discriminator, and maybe at this point, right, the discriminator didn't have to work that hard to distinguish these images. Maybe it was using some really coarse statistical properties to tell them apart. So it's still not doing a great job. It's like fooled by this not very convincing digit. So once again, we update the discriminator. We say, hey, that top one is fake, the bottom one is real. Update your parameters. Generate another image, take another real image. Now the discriminator knows the difference. And we'll feed this once more into the generator, say, hey, make stuff more like the stuff on the bottom than the stuff on the top. And now maybe the generator is able to make quite convincing digits that are going to be sufficient for our purpose to say, here's a fake digit, we can make fake digits all we want. And the discriminator can't tell the difference because they're good enough. Okay, so you might be thinking, okay, here's our framework for generating synthetic data. So now we're good. If you make synthetic data, it's all private. But as I said earlier, right, that's not necessarily going to be sufficient. Why not? So we actually have to make the generator network model private. And there's a question of what it means for a model to be private. This might seem a little weird, right? But the reality is that models essentially memorize facts about training data. And you can use that fact to basically extract information about the training data that was fed in to train the network. So you can often reliably guess whether a record was included in training or not, which violates differential privacy, right? You shouldn't be able to tell whether my data was included in a data set based on the model. Now you might think memorizing facts, that sounds like overfitting, right? So maybe we can just do some regularization. Maybe we put a penalty on the size of the weights. Maybe we do dropout. But unfortunately, techniques for preventing overfitting just aren't quite sufficient to actually protect individual level privacy. So what can we do instead? So there's at least like 3 broad approaches that you can see out there in the literature for making models private. The first one is to add noise to the training data. But as I said at the start, right, if you add noise to the training data, the amount of noise you have to add is just so massive that it basically kills any utility that you had. So it doesn't really work. You can add noise to the trained parameters. So you run your model, your neural network or whatever like normal. You get out some parameters and then you add some noise to the end of that. This like kind of works, but again, the amount of utility you lose, the amount of information you lose is larger than you would really want. And so the last technique, which is typically the most effective, is to add noise to the gradients during training, right? So the gradients are just the things sort of feeding the information back to the network, telling it how to update itself. And what we say is you're not actually going to get the fully faithful information about how you should update. You're going to get a slightly modified, slightly noisy version of that. And so thinking back to the example with the Betty White average age example, right? There, her contribution as a single record to the average was negligible relative to the noise, and that was what guaranteed privacy. And here, the contribution of any one record to the gradient is going to be negligible relative to the noise, and that's what's going to ensure privacy for the trained network. So this overall approach was proven to work for generative adversarial networks by a paper last year. So adding noise to the gradients plus a couple of restrictions on what the architecture looked like is enough to make generative adversarial networks differentially private. And so I took this model and implemented it in an open source Python package using PyTorch. In theory, it's compatible with any kind of data that you might have, although I have some helper tools to make this easier to do with categorical data sets. So the code is online. If you want to take a look at it, you can play around with it, try out some examples, see how it works. Okay. So I've gone over some basics of like generative adversarial networks and differential privacy, but now the question is like, does any of this stuff actually work? So in the last part of the talk, I'm gonna give an example using data from the US Census, make some synthetic data and see like, does this approach actually work? So a little bit of background on the data. The data I'm looking at comes from the American Community Survey, or ACS. And as part of that, the census releases individual level data known as the public use microdata sample, or PUMS data. So I took the 2017 ACS PUMS data from the state of Illinois, and I looked at 4 variables from this. So age, which I binned into 9 categories, marriage, which comes in 5 categories, means of transportation to work, which comes in 12 categories, and schooling, which comes in 24 categories. So here's just an example of some like randomly selected entries from this data set. At the top, you can see someone who's between 56 and 65, has an associate's degree, is widowed, and drives to work. You can see a 26 to 35-year-old who has a bachelor's degree, has never been married, and takes the subway to work, and so on and so forth. So there's just a whole bunch of records that look like this corresponding to individual people in the state of Illinois. Okay, so how do we take this and turn this into some synthetic data? So there's about 600,000 input data points in this data set. First, I convert them to a one-hot encoding, so just for the sake of the network. So for each level of the category, there's just a column, that's a 1 or a 0, depending on whether that record falls within that category. Then I create a generator network and a discriminator network, and I'll talk about the architectures of those in just a second. I train the GAN, or generative adversarial network, so the package takes care of most of this for you, and then generate the same number of output data points as there were in the input. Okay, so here's a quick illustration of the generator architecture. So at the bottom, you have this like bell curve representing the Gaussian noise that is the input to the generator. That gets passed into a fully connected layer that maps to some hidden units. You pass that through a nonlinearity to do some thresholding. And then you have this sort of ugly, complicated architecture where you have fully connected layers plus this Gumbel softmax. And that's going to be the thing that basically maps from these hidden units onto the categories that we want as the outputs. So it's sort of a multi-output model with an output for each category. So age, marriage, transit, schooling. So what does this look like in code? For this package, right, you can just implement all of these things as PyTorch modules for the neural networks that you're building. So here I've just used the sequential module. So there's a linear unit, there's the nonlinearity, and then I wrote a PyTorch module in this package to just make handling this like multi-category output a little bit easier. And then you also have to define a function to create the noise that's the input to the generator network. So this is pretty simple. It's just Gaussian noise. And so as for the discriminator architecture, you'll notice that the input of the discriminator architecture is the same as the output of the generator architecture, right? Because the discriminator is going to be taking this generated data and also real data and trying to say, is this real or not? We map through a fully connected layer to get to some hidden units, pass that through a nonlinearity, and then map the results of that down onto a single value that's going to be our representation of whether the discriminator thinks this is real data or not. So it's like assessment of how good this data is. And so again, the code for this is just going to be another PyTorch module, our linear layer, our nonlinearity, and then our linear layer mapping down onto a single unit. Okay, so once we have on the left all of that code set up, it's pretty simple to put this into the GAN and train it. So first we just pass the generator, discriminator, and noise function into the DPWGAN class. We train it on the real data set, and then we generate data of the same size as the input data set. Okay, so before I show you what the generated data looks like, I'm going to show you some of the real data again so that we can see like a side-by-side comparison. So here's one way of looking at the real census data. This is a cross-tabulation showing counts for age and marriage as categories. So on the y-axis, you have age increasing from bottom to top. And on the x-axis, you have marriage categories, so never married or under 15, married, separated, divorced, and widowed. And then in each cell, you have a count of the people who fall within that category, that combination of categories. And then the coloring is just showing you in a visual representation that same sort of count information. So the darker the cell is, the more people who fall in that category. So you'll notice, right, like there's this large concentration in the bottom left of people between the age of 0 and 17 who have never been married or are under the age of 15. That makes a lot of sense, right? You can see that there's sort of a concentration, an increasing concentration of married people as you get a little bit older, so 26 up through like 66. And then, if you look up in the top right corner, you can see that like people are more likely to be widowed as they get, much older. Okay, so that's what the real data looks like. So now I'm going to show the same crosstab on the right for the synthetic data. And what you can see is, right, that to a first approximation, these look extremely similar, right? Like the basic heat map is extremely similar, same areas of high heat, same areas of low heat. And so we've captured most of this, a lot of this correlational information that you saw in the original data. So we know that most young people have never been married or are young. We know that sort of marriage increases as people get older. We see that, widowing increases as people get much older. So, I think to a first approximation, we've done a very good job of capturing the information in the original data. Now, of course, it's going to depend on your application, whether some of the discrepancies here are large enough to be of concern. But I think this shows that, again, the basic approach is largely working. Here is means of commute to work versus age. So on the y-axis, you have a whole bunch of commute categories: bicycle, bus, car, truck, van, and so on and so forth. And then age categories. Not quite as much information in this graph. What you can largely see is just this one really dark line. That's because basically everyone in Illinois drives to work, unfortunately. So, but again, you can see that the information, the broad contours of the information are largely captured. And then just to show that this even works with a really large number of categories, I know this is a lot to look at. I don't expect you to see everything in it, but this is schooling versus age. So on the y-axis, you have highest degree completed from like no schooling up through doctorate degree, and then again, age on the x-axis. And what you can see is, right, like most young people are in grade school, not a whole lot of like 17-year-olds with doctorate degrees. And of course, the synthetic data is capturing that as well. And then again, some other patterns with respect to the distribution of like high school diploma, bachelor's degree, and so on. So to sort of sum up, differential privacy is a useful framework for understanding individual level privacy. So differential privacy limits your ability to tell if someone's data was included in your data set, and it also limits what you can learn about someone because their data was included. And so that's a very powerful guarantee. Additionally, generative adversarial networks can be a great technique for making fake data. So we saw that we can make this data that kind of looks like the real stuff. And by combining these two approaches, you can make useful data sets that researchers can potentially use, but that also protect individual level privacy. So again, this code is all online and open source if you want to try it out yourself. Both the census data and example that I used in this talk is in there, or you can try it on your own data sets. And then I have at the bottom my contact information and again the slide link in case you missed it. So now I'll take questions.
So basically when the assumption is that you're preserving statistical information, is there any sort of proof to that, or are you just kind of assuming that the discriminator does a good enough job?
Yeah, so there are sort of mathematical proofs that the generative adversarial network should learn to match the distribution of the original input data set. So in that sense, there's a guarantee. In practice, like GANs are like this complicated dynamical system, and so it's often hard to like actually prove or meet convergence. And so in practice, you might not actually like capture the input distribution. And then also like what you can capture in the input distribution depends on the architecture of your network. So if your network has the capability of representing the input distribution, then it will be able to capture that. But if it doesn't have that capacity, then it won't. So it's some combination of like, I think ideally if you were actually doing this in practice, you want to like do some diagnostics afterwards to like make sure that this has gone okay. You can also start by training the network and tuning the network without the noise and privacy so that you can do all of your like fitting and optimization there, and then add the noise in so that you're not like breaking the privacy protections by like overfitting the private data to the real data. So yeah, like in practice, there's some mathematical guarantees and proofs, but like in real world applications, not exactly.
So for the Betty White example, I know after you added the noise, like her age was obviously not real, it was like 150. But I wonder if you could infer that she is like older because it does skew towards being older.
Yeah, so that's absolutely right. There is a sense in which it leaks some information about her. So the way differential privacy works is the amount of noise you add sort of influences how much you can learn about someone, right? And so if you were very concerned about that and wanted to make sure that someone couldn't even learn like that someone was at all like on the older range, you would need to add a bit more noise, and that would decrease your utility a little bit. And so like differential privacy is not a guarantee that you can't learn anything about someone, but what it is sort of a limit on how much you can sort of inform your distribution, and that's going to depend on how much noise you add.
Yeah, so like the example which you showed us was more about the categorical data, but then I was just curious to know if you have tried this with like quantitative data and how does it perform?
Yeah, so a couple of things there. So one of the reasons that I was looking at categorical data is that actually most of the literature you see out there on GANs and differential privacy is looking at things like images or other kinds of continuous data. So I was actually very curious like how these would perform with categorical data. That being said, continuous data like images is a little bit different from like continuous data like real values. So you'll notice that I binned age, but you could make the argument like maybe that's not really the appropriate way to treat age. And I haven't really played around with that yet. The other thing I'll say is that sometimes this particular technique can be finicky if you're mixing categorical and continuous data. So I don't really have a great answer for you there, but it's definitely something that I'm interested in exploring more, whether you can really make this work in a unified framework with both continuous and categorical outputs.
And just one more question. So like behind the covers, do you know like because like the categorical values has like one of the two, 0 or 1, so behind the covers like when it generates the fake data, what does it represent as?
Right, so it's generating those like one-hot encodings as the output, so the 0 or 1 within the categories, and then those just get mapped back onto the categories. So there's some information potentially being thrown away, especially with ones that have levels. Ideally, the network is like doing some feature engineering and learning that information. In practice, I have like a pretty shallow network that probably can't learn that kind of representational information. But if you had more sophisticated and rich data, you could potentially like hope that the network learns those features or like enforce some of that information into the structure of the network.
Have you tried like other neural network, like variational?
No, so in this case, I've just tried like this particular, I mean, I fiddled with the architecture a little bit, but I haven't played around too much with, in theory, you could use any kind of network. In practice, the structure of the network informs like how much noise you have to add and things that you do with the weights. And so some networks are going to require sort of more noise, and that might mess with your utility a bit. But the package, again, is written in a way where like you can throw in any PyTorch module that you want. So it's easy to play around and experiment with other types of networks. One more? Did you have? Is there time for one more? Last question? Yeah.
So there's a lot of like upcoming litigation about how much data companies can store and maintain. Do you know if any court has like ruled on this, whether this is an acceptable form of anonymity and privatization?
Yeah, so I'm not aware of any court cases looking at this specifically. I think there's a few things. So first of all, some of those new regulations regulate collection of data. And so the approach that I've discussed here assumes that you've already collected the data. There are differential privacy techniques that like basically apply the privacy before the data is collected. And so in that case, that might be sufficient. But a technique like this that isn't designed to do that would not satisfy those requirements. Beyond that, I think, you know, I doubt that any legislation is going to be written in a way that that can fully like decide this question. And I think there's probably just going to be a long process of us figuring out like what is an acceptable level of privacy for accomplishing the goals that we care about with that legislation. I know that's not a super satisfying answer, but I think this is all just sort of starting to get worked out. Great, thanks everyone.